Right. Check. Right. All right. Welcome everyone to the last lecture for me until 4 weeks from now, when I will come back to teach about clocks. Yes, so the goal of this lecture is to complete the example that we started yesterday of the simplest autonomous thermal machine, the 3-qubit refrigerator, to talk about the steady state, to talk about heat flow in the steady state, to talk about the notion of efficiency of the thermal machine and what the limits to efficiency are, and the end result of being that, in fact, the normal Carnot efficiency that you have used to describe classical thermodynamics machines actually is the relevant thing here as well. Okay, so to pick up where I left off yesterday, I discussed the steady state of the Lambladin equation. I will write the Lambladin equation as we go through again to remind you, but the steady state was of this form. It was the thermal state, the initial thermal state. Now, I just have to say, I wrote this following the notation of the paper it's taken from. I'm using the ordering that the cold system is the first, the room temperature system is the second, and the hot temperature system is the third. So when you see 1, 2, 3 here, it means that, and that's the same ordering that I used yesterday. Okay, so the steady state is the thermal state, which you can think of as the initial state before the machine is switched on. And by the machine here, I mean the interaction Hamiltonian, plus some term delta times a sequence of operators. And we discussed how we can get the operators yesterday. We simply take the thermal state, we put it in the Lambladin, we see what operator we get. Then we take that operator, we put it in the Lambladin, we see what operators we get. And in the end, we get this set of operators that when you put them into the Lambladin, they simply give you something else in the set. And the operators are of this form. Either you have, oh, sorry, there is a mistake here. That was supposed to be, you want to, that's Z3, sorry. So the operators are either of the form thermal states on 2 tensor a sigma Z matrix, this is the Pauli Z matrix on the third, or thermal state on 1 times a Pauli matrix on the other 2, or just the Pauli matrix on all 3 of them. And then there's the Z and the Y one. And how do I get these Z and Y operators? They come from the form of the interaction Hamiltonian. So I'm in the eigenbasis that is determined by these 2 states, this one and this one. These are the 2 states that flip to each other in the interaction Hamiltonian. So I can think about it as the following, actually. I can say my H interaction, in fact, is of the form G times X1, 2, 3, because X1, 2, 3 is the Pauli X operator. The Pauli Y operator, then Y1 to 3 is given by the usual form, Z1 to 3 is given by that form, and then the Z1, 2 and the Z1, the reduced Pauli matrices are simply gotten by tracing over the Pauli matrices, the Pauli matrix that I started with. Now, one thing to note here is that the Z that I have is not the same for the cold, room, and hot systems. You see on the cold and the hot system, it looks the same, but on the room one, it's sort of the flipped, it has the flipped version because you have 0 with the 2 1s or 1 with the 2 0s. Meaning that when I get, so Z cold and hot, if I trace out 2 and 3 and just end up with Z1, which is the same as Z cold, I can write it as Z1, or if I trace it out to get Z3, I will get the same thing. I will have 0, 0, minus 1, 1. But if I have Z2, which is where I trace out 1 and 3 in this expression, then I'm actually going to get the opposite, 1, 1, minus 0, 0. And this, of course, makes sense because these operators, the sign between these 2 operators refer, because of the fact that the energy transfer in the first and the third system is the opposite as the second system. The second one lowers its energy when the first and third gain energy. Okay, the last thing to say there is that this bias delta was given by, in the initial state, the value of P010, 101 minus P010. I'm not entirely sure whether I wrote this yesterday with a negative sign or not, but this is the value of delta that we're going to use today. Okay, and then now you can take this steady state, and of relevance to us is what are the actual states of each of the systems. The most important thing, of course, is the cold system. because this is the one that we're trying to cool. So we want to see whether the end temperature in the steady state is actually a smaller temperature or a higher inverse temperature than what we started out with. And so if you do the trace on all of these, what you end up getting is something of this form. So rho I is going to be given by tau I. So I goes now 1, 2, or 3. And then you have, again, you have the delta term. You have some constant, which I'll just call C, divided by gamma I, Zi. Now, gamma I is the, I will write the Lamblardian in the next board shortly. Gamma I is the constant associated to the dissipator of heat bath I. So it's basically the coupling constant of system I with its own bath. Okay, let me remind you what the Lamblardian is now, because we will refer to it. So the Lamblardian, so put it this way, d rho over dt is given by the Lamblardian acting on rho, and that is minus I h int on rho plus the sum over, let's say, I belonging to, sum over I, let's say, well, I belong to 1, 2, 3 here. Gamma I, and then the dissipator, and if you remember correctly, the dissipator form was trace away the I part of the state, bring in back the thermal state of I, minus the state rho itself. Okay, so there, now you see what the role of gamma I is. Right, okay. Are there any questions? No? All right, so the first thing we would like to see is, okay, when is it that I have cooling and when do I not have cooling? Okay, and so now we, in order for the first thing that we check is now what we can call the cooling regime. What set of parameters do I need in order for this to act as a fridge or to not act as a fridge? And so to do that, I just look at the state of 1, which is C. So rho 1 is equal to tau 1 plus delta times C times gamma 1 times Z1, and I can write Z1, I've written it up there. This is 0, 0 minus 1, 1. Now what you see is that this is the thermal state that I started with, and then I add something, the delta times this operator. Now this operator corresponds to cooling, because it's an operator that increases the ground state population and decreases the excited state population. So if the thing that multiplies this operator is positive, then I know that the resultant state is going to have a larger value in 0 than just the thermal state on its own. So I need, so rho 1 is, let's say, cooler than tau 1 if and only if delta is greater than 0. Okay, so now let me see what delta is. And so the delta is equal to P10 minus, okay, so I can actually simplify this. If delta is greater than 0, that is the same thing. I use the fact that it's given by that difference, and I can put it in another way. I can say P101 divided by P010 must be greater than 1. So the first term has to be greater than the second term. But this is something that we now can calculate, because remember that these are the populations in the initial state. So this is the initial state ratio of these two things. But the initial state is just the product state of 3 thermal states. And so the populations will factorize into P1 of the cold times P0 of the room times P1 of the hot. And down here we have P0 of the cold, P1 of the room, P0 of the hot. And so each of the ratios then becomes just the Gibbs ratio. So this now should go upwards here. P1 upon P0 for the cold one becomes e to the minus beta cold E cold. P0 upon P1 for the room is e to the plus beta room E room. And P1 upon P0 for the hot is e to the minus beta hot E hot. And this has to be greater than 1. Okay, which implies, and now this is the final equation. I just If this is to be greater than 1, then if I unexponentiate it, the resultant thing has to be greater than 0. And so I end up with beta cold E cold. I can also flip it by flipping the minus sign. So this is less than beta room minus beta hot E hot. And I can take EC over to this side, and I just have this equation here. But this is something that you will have recognized, hopefully recognized. When we constructed the refrigerator in the beginning, we looked at just the two qubits room and hot together as a composite system. And we could see that there was a qubit in there, the qubit between 1, 0 and 0, 1, that was really the one that was interacting with the system, the cold system. And we looked at the virtual temperature of what that qubit is, and that is precisely this expression that we have, beta V, which means that our end result is just that beta cold is less than beta V, which makes sense. This is the whole point of understanding these in terms of virtual temperatures, is to see that in spite of looking at it as a complicated interaction Hamiltonian between three different states, what you can understand it in the end as is one qubit that interacts with a virtual qubit of another system, a composite system. And we have a refrigerator as long as the thing that we're trying to cool has a virtual temperature that is warmer than the one that we've connected it to. So we've generated a virtual temperature that is colder than C, and so we have a refrigerator. Okay. Yes?
What's the C and
this? So they are all the C and all of those Q1, 2s, and Ks. They are complicated functions of essentially the in the Lindbladian, the gamma here, and in the etchant you have a G. They're just functions of that, and they're reasonably complicated. I mean, in the lecture notes there's the reference to the paper that to take it from. So there you can see the exact form of them. But well, the interesting way of writing, I write it this way because I separate the part that just depends on those parameters from the part that depends on the populations of the initial state. And so you have that. Yeah. But it is interesting to also look at them because, for instance, you can ask, what is the state of the machine if I make one of the coupling constants very weak, if I make G very weak, the interaction very weak, or if I disconnect one of the baths, so I take that P to 0, and then you would, some of those terms would become 0, some of them would disappear, and then you have the limiting cases, for example. So yeah, they are important, but just to check whether it's cooling or not, you do not need them, which is also quite powerful because you could imagine that I have to match the rates in a certain way in order to make this cooling refrigerator or not, but it turns out no. As long as the two levels that you've coupled have the initial states with populations a certain way, then that's enough to check it. Yeah. Okay. So the next thing, natural question to ask, since this is a thermal machine, is what about heat? Sorry? Yes?
It's obvious that the procedure of plugging in operators into the plugin will result in a finite set of such and such that the steady state is a linear combination of both.
So there are two answers to the question. So because the density matrix is a density matrix of 3 qubits, it has 64 elements. And so we know that for sure, if we chose 64 linearly independent matrices, we would definitely be able to write any solution as a sum of those 64. The reason we do it this way is because we expect the final density matrix to actually be quite simple, because thermalization tends to just take away all of the off-diagonal elements. And the interaction Hamiltonian does have an off-diagonal element, but it's only in one single subspace. So we expect that the steady state solution would have a lot of zeros. And this is why we start the procedure of putting tau 1, tau 2, tau 3 into the Lindbladian, because we expect that when we go through this procedure, the number of operators will be much less than the maximum. And so it turns out in the end that we have 9 operators instead of the 64. But yeah, so the question is not so much, there will definitely be a finite set just because it's a finite dimensional system. but in general, we do it because we expect it to be a much smaller set. All right. Yes. So how do we calculate the heat flow? And yes, so if I ask now, what is the heat flow between bath 1, 2, or 3? There are 3 baths, and let me say, what is the heat flow between bath 1 and the cold system? And that would be the question. So the first thing I can do is I can look at the Lindbladian, where is it? Which is here. And I ask, well, what are the things in the Lindbladian that actually cause the energy of the cold system to change? And the answer is there are only 2 things. One is the interaction Hamiltonian, and the other is the dissipator on cold. Because if I put the cold system into any of the, if I put rho into any of the other dissipators, the cold part will not change. Because remember, what the dissipator does is it only changes the part of the state that is connected to bath I, doesn't change the other 2. So basically, I have 2 competing processes, which is so on system I, let's say on C, which is the dissipator on C and etchant, out of which the dissipator on C is heat from the bath, and etchant is an energy transfer within the state. Okay. Now, I didn't say one thing before this, which is important. When we get the steady state, it's important to know that note that a steady state in a thermal machine is not the same as nothing is happening. Actually, the steady state is more that there are many competing processes, and the result of those competing processes is that the system has reached equilibrium where all of the competing processes match each other. And so in particular, there is a positive heat flow. Just because the state is not changing does not mean there's no heat flow. Okay, so how do we calculate now the heat corresponding to that dissipator? Well, we simply isolate the term in the Lindbladian, because in order to calculate in general the rate of energy change, we would plug d rho by dt into the Hamiltonian, take the trace, and that would give us the energy change. But of course, the global energy is not changing. We only want the part of the energy that is changing due to the dissipator on C. So in the end, what we get is that QC will be equal to trace of HC. So this is the local Hamiltonian of C. I haven't written it in the Lindbladian because, as I said yesterday, we went into the rotating frame. So we did not need for the evolution of the system to consider the Hamiltonian. But now when I want to consider the energy change in C, I calculate the Hamiltonian of C times the dissipator of C on acting on rho. So this will be gamma C times trace over C rho infinity tensor tau C minus rho infinity. That's that, and this is the heat from the bath. One must always, once you write something like this, determine this with the sign of the flow. Because I've written it as a change in energy of the system, if this is positive, it means the change in energy of the system due to the dissipator was positive, which would mean that there was a positive heat flow from the bath. Okay. That was an irritating place to run out of space. I need a new board. I will want to keep this. And where's the rest? Let's see if this works. This. Okay, let me see if I can do without erasing that. Okay, so, right. Now, when I write HC, of course, it is implicitly assumed it's HC is only on C, but the full form of that is HC, tensor identity on room, tensor identity on hot. It's the full form of the Hamiltonian on C. Because it is of that form and it's an operator that doesn't really act on room and hot, when you do this calculation, the room and hot parts actually disappear from the right side of the trace as well because they do not change. So in the end, what you end up getting is that QC is equal to gamma C times HC times, trace over C, HC, and in the end you have tau C minus, I'm going to say rho C here, and this is again rho C infinity. I actually write this as rho I infinity. The reduced state of the cold system when you look at the steady state. And that in turn, I can use now this formula, rho infinity for each of the subsystems itself is the thermal state plus something. So this thermal state is actually going to vanish there. And I'm going to get minus gamma C. Oh, sorry. So the thermal state is going to vanish because I put tau I here. So tau C will cancel with that. And then I have delta C Zi by gamma C. So the gamma C also cancels. And I end up with minus delta times C times trace of HC times ZC. ZC, recall, Z is 1. So Z is written with 0 minus 1. And so when I multiply the Hamiltonian, so the Hamiltonian, just for reference, the Hamiltonian of C is going to be 0, 0, 0, EC. So it's EC 1, 1. And so then I'm going to get, with a minus, I'm going to get positive C EC. Okay, so it's proportional to the energy gap of the cold system times the constant C, and C, as I said, just like the other constants, they depend a lot on the rates, times that bias delta. And this is, again, something we would expect. We already have checked that if delta is positive, it acts as a refrigerator. And so now we see, for consistency, if delta is positive, we get a positive heat flow. Okay. I can do the same thing now for Q room and Q hot. And as you might suspect, I end up getting something very similar. So I get Q room is minus delta times C times E room. And I will get Q hot is positive delta times C times E hot. The reason for the minus sign, mathematically, of course, is because the Z operator for the room has the flipped sign. Physically, we know it because of energy conservation. The only way for heat flow from cold and hot to be positive is for the Q room to be negative. And we can verify this by now writing these down as a sum. QC plus QR plus QH, you can verify is equal to, well, it's going, I can write it in 2 steps, delta C times EC minus ER plus EH. But we choose by construction, ER is equal to EC plus EH. I mean, I wrote that down yesterday. I haven't written it down today, but the room is equal to EC plus EH in order to make everything energy preserving. And the result is that this is 0, which is again a consistent result. If you have the steady state and the state is not changing, then if there's any heat flow into the state, it must be balanced by a heat flow out of the state. So the total heat flow into the state must be 0. What is also important is to see another way of writing these 3 things is to say that the ratios QC versus QR versus QH is exactly the ratio with the minus sign of PR. Okay, so yes?
From the equation up there, so where did it trace?
Well, I didn't do this explicitly, but basically, so in the parentheses, you have trace of rho infinity tensor tau C. Okay, so that is a state where put it this way, if you just look at the diagonal elements of that state, the difference is not in the C, is only in the C part, it's not in the R and the H part. And the result is that when you multiply it by an operator that is just identity on the R and H part and something non-trivial on the C part, then all of the R and H part just go away. I haven't done this explicitly, but this is what you would get essentially, because you have trace of identity times that part. So it, yeah, I would, perhaps you can try it as an exercise. Just go trace of an operator tensor identity on a second system. And then you have two things, one of which is just a complicated row of the two systems. And then the other thing is you trace out one of them, replace it with whatever you have, and keep the same thing on the second system. And you see that the second system basically goes away. This is also, okay, put it another way, this is also the reason why when we write measurements on a one system, which is part of a global system, we can start by writing the measurement operator as measurement operator tensor identity on something, but then because it's identity on that something, it just vanishes because that's trace one, essentially. It comes from trace of identity on room tensor any matrix is one, so that all just vanishes there. Okay, so we have the heat flows, and so the last thing now that we want to ask the question about is, what is the efficiency? So what is the efficiency of a refrigerator defined as in the first place? So for every thermal machine, we typically have a useful quantity that denotes how well it's doing, and a resource quantity that denotes how much we're putting into it. And in the case of the refrigerator, what is useful to us is QC, the heat that we draw from the cold bath, and the resource that we put into it is QH, because the room temperature bath is assumed to just be your environment. It's something that comes for free. But the resource is really the hot temperature bath. The only way you can generate it when you only have access to an environment is by burning fuel or consuming energy in some form. So these are the resources. So the efficiency then is just given by the ratio of these QC by QH. And this is really a classical thermodynamic expression. It's not something I'm making up right now. But now we know from the construction of the thermal machine that in fact eta is given by EC over EH, because QC and QH have the same ratio as EC and EH. Okay, so that is our efficiency. It looks like it's a ratio of two quantities that we could make as small as or large as we like, because we think, well, EC may be given to us, that's the system, but EH we could tune as we like. But we cannot, because we have one constraint, that it has to actually act as a refrigerator. So the constraint for us is that that condition that we've written, BC less beta C less than beta V, always has to hold true. And so now what we can do is just massage that constraint into something useful. So let me take the form of the constraint there. So I'm going to write it as beta EC is less than, and on the other side I have beta R. I'm going to write ER as EC plus EH. And then I have minus beta hot, E hot. So I've just rewritten now the constraint up there, down here. And now I can rearrange terms. I have, sorry, beta C minus beta R EC. So I've taken the terms with EC on the left-hand side. I keep the terms with EH on the right-hand side. Is less than beta room minus beta hot E hot. But this gives me EC over EH is less than beta R minus beta H upon beta C minus beta R. And this, you may or may not remember, is actually the Carnot limit for a refrigerator. So in classical thermodynamics, when you study refrigerators, you actually get that expression as being the maximum efficiency that a refrigerator can have. And we have just re-derived it in the, well, at least we have arrived at the same one in the context of the simplest quantum refrigerator that you could construct, just consisting of 3 qubits. Okay. Another thing to note is that just like in classical thermodynamics, the only way to reach this limit, so if you try to get EC by H to be this value, then that would mean that you were essentially getting close to this being an equality, which is the same thing as getting close to the initial one being an equality, which is the same thing as getting delta, that term there, which was supposed to be greater than 0, to be very close to 0. But when delta is very close to 0, remember that all of the terms that we have, the heat flow and the change in the steady state from the initial state, they're all proportional to delta. So just like in classical thermodynamics, as we get closer and closer to the Carnot limit, our machine becomes closer and closer to actually doing nothing. So at the Carnot limit formally, your machine actually does nothing. So if we pick delta equals to 0 and beta C exactly equals to beta V, that would mean that we were coupling a cold system to a virtual temperature that was exactly the same. So no heat would flow. So the theoretical maximum efficiency is only acquired at the limit of complete reversibility, which is also to say that you don't, complete reversibility is another way of saying zero power. All right. Are there any questions? None? All right, so then I will take 5 minutes to discuss other types of thermal machines, and then I have some questions. So, so you don't want me to ask about the visitors? Very good. All right. Thanks. Okay. So other thermal machines. So what we discussed here is a refrigerator, but we can now do very similar things in other contexts. So one generalization of doing this is to say, well, I don't really need to do this only on qubits. So one very easy thing you could do is, instead of taking qubits, you could take harmonic oscillators. And in fact, the whole model that I've discussed now was predated by somebody doing this for harmonic oscillators. So in the case of a harmonic oscillator, once again, so you can have 3 harmonic oscillators, and then you would say, well, how would I couple these 3 things together? You exactly use the same principle. So if the harmonic oscillator here has frequency omega C, this one has omega R, and this one has omega H, you do 2 things. You say, well, let me choose omega R is equal to omega C plus omega H. So this already introduces some sort of energy conservation into the picture. And then the next thing you say is, well, I'm going to now use an interaction Hamiltonian that basically generalizes that, or is the equivalent of that, but for harmonic oscillators. So what would that be? You would have an H int is equal to A dagger C, A R, A dagger H, plus the Hermitian conjugate, A C, A dagger R, A H. And I can, of course, multiply this by any constant. Okay. In the case of harmonic oscillators, the reset master equation that I discussed is actually not a valid master equation. So then what you would have is really, you would have Lindbladian terms. So my dissipator, let me fit it here. So D, let's say C on rho. Oh, I'm not going to write it on rho. I'm just going to write it on the state of rho C, for example. Because whenever you have a dissipator on one system, to write it on a general system, by now you will know what the form is. I just trace out only the part that I want and replace it with the thing. But the dissipator on rho C will be the sum of 2 things. Okay, I'm going to need more space. Never mind. I'll put it here. I'll put it up. So this is beta on C is going to be, so gamma plus, and this is now of the Lindbladian form, gamma plus dagger minus half gamma plus dagger. So I'm going to write as gamma minus. So gamma plus is equal to gamma minus dagger, comma rho. And then, so this is with, let's say, yeah, gamma plus gamma minus, and then you have the other one, gamma minus rho, gamma plus. Well, why did I write it as gamma? I have written A. Sorry, I don't need to write it as gamma. I can just write it as A. This is A dagger is the raising operator A, sorry, A dagger A rho, and then on this side I have A rho A dagger minus half of A dagger rho. Okay, so this is the Lambdadian form that we discussed yesterday and that you would have done in a tutorial. You have a jump operator and the dissipator corresponding to the jump operator is that. And so you can see clearly that the first part of the Lambdadian corresponds to raising the energy of rho because it's A dagger rho, then A dagger dagger. The second part corresponds to lowering them. And because it's a thermal Lambdadian, it will satisfy detailed balance, as I discussed yesterday, where gamma plus by gamma minus is going to be E to the minus beta C, in this case, omega C. There are some units. So omega C is not a frequency, it's an energy. So there are units where h bar is equal to 1, say. Okay, but what we've done here is constructed in spirit, at least, exactly the same thing that we had in the 3 qubits. You have 3 frequencies. You've chosen the frequency so that you have energy conservation. You've created the interaction Hamiltonian with this. And the result is that, so if you did the calculation for, is this a refrigerator? Are we in the cooling regime or not? You would get exactly the same thing as we got there up there. It's just that you place the E's by the omegas here. So we'll have exactly the same condition for cooling. And in that regime, you could then calculate the steady state. Now, the steady state, of course, because it's harmonic oscillator and population is spread out, there are going to be some numerical differences. But whether it's a fridge or not, what is the efficiency and what is the Carnot limit, all of that will remain the same as it is for the 3 qubit fridge. Okay. So that's the first thing you could generalize to. And then we can also consider, instead of a fridge, imagine that we wanted to create the other very important thermal machine, which is an engine. Now, when we are discussing engines, we now think about work, because the whole purpose of an engine is to create work. And how do we create work? As I've already discussed in the lecture on erasure, when we consider work, we need to have a system whose entropy doesn't change. So qubits are not actually ideal for this. What we would like instead is to have something like a ladder where you could have a broad space of states. So the way we construct an engine is to have 2 qubits as a machine, we can say. And this is very much similar to that, the fridge. If I look at the fridge in another way, I can consider it as the cold is my system and the room and hot is my machine, and the machine acts on the system. So again, I'm going to have my room and my hot, or a hotter temperature and a colder temperature as my machine. And then they are going to act on a ladder. Now, I can construct the ladder as being a finite ladder. I can construct it as being bounded from below. I can construct it as being unbounded from up and below. Unbounded from up and below is unphysical, but at least you can do calculations that give you sort of the spirit of how this works. The same way as up there, I will choose the energies to match. But as I discussed in the last lecture, when you're constructing a fridge, you need the room to be larger than the hot, because the way the fridge works is the room accepts energy from hot and cold. When you construct an engine, you need the hot to be the largest energy, because your hot is going to give energy to the room temperature as well as to your engine, to your work source. So this is now going to be the hot one. This is now going to be room. And this is, I just call it W. And we're going to have that EH is equal to ER plus EW, where EW is the energy gap here. The rest of it goes very similarly. So the transition that we would like is this transition. This one goes up, this one goes up, this one goes down. The transition that's not so favorable to us is the inverse. Okay. How do we get one transition? How do we get this to work? Well, we write an interaction Hamiltonian between the 3 as H int is equal to, and now we will have, so let's say 1, 0, 0, 1 on hot and room. So this is when the hot goes from 0 to 1 and accepts energy from the room and from W. So this will be the lowering operator on W, plus the Hermitian conjugate, of course, 0, 1, 1, 0, tensor, gamma plus on W. And of course, I can multiply it by a constant G. Here you will have a dissipator for H. You will also have a dissipator for room, but the work source has no dissipator typically because you consider it as a work source. You could complicate matters and add a dissipator there that will just add one more degree of complication to the model. But in principle, you could start just with these ingredients. So with H in THDR, you could now calculate something here. The key difference between the engine and the fridge is that if I have, for example, an unbounded ladder, I'm never going to reach a steady state. So it's going to, the population is going to spread on the ladder and it's never going to reach a steady state. So the steady state is not what I'm looking for. What I look for in this case is what I would call the asymptotic rates. So I go, well, if I start this engine and I let it run for a while, after a while, what do I see the rate of the energy increase in the engine be? So the asymptotic rate limit as t goes to infinity of d of the average energy of EW. So, okay, let me write it as this, the expectation value of h of W by dt. So that is one thing. And the other thing that I would be interested in, because I know there is a transition that is favorable to me, there is a transition that is not favorable to me, and they are going to compete with each other. Of course, if I run this in the regime where it is favorable, one of them is more probable than the other, but it's still a biased random walk. So I'm still going to spread. I'm not going to go up deterministically. So another thing that I could look at is also limit of t tends to infinity of what is the rate of change of the variance. Here, pH is equal to PR plus W of the variance, and of course the variance is h squared W minus h W squared. Oh, I've already written d by dt. I have to write it again. Okay. So I can do this as well. Right. And yes. That one? For the harmonic oscillator, I only wrote it for the cold one. Sorry, yeah. So this is C. No, this is just actually no. This is the whole row. Yes, it's fine because if I'm considering it on the whole row, then each of these AC daggers will just be tensored with identity on room and hot. Yeah, yeah. So yes, so yeah. So each of these would be AC dagger tensor identity on room and hot, and so on. And that would be just a dissipator of C acting on rho, and then I could have the equivalent ones for room and hot. Good. Yeah. Oh, yes. So the raising and I do not remember the exact. So the raising and lowering operator that I've written here, gamma, when it's a simple ladder, is really the raising is the operator. So gamma plus on W is the sum over all n of n plus 1 n. So if you put in the state n, it is going to give you the state n plus 1. So it just goes up the ladder. In the case of the harmonic oscillators, it's the same, except that in addition, you have some constant in front of that depends on n. So it has square root of n and stuff. And I do not remember this because it's been a while since I've done harmonic oscillators, but they are still, you increase in energy or you lower energy. All right. I do remember that A dagger n is the number operator, so you end up getting n, but that's about it. Okay. Yeah, so actually, I'm going to conclude here. I'm going to leave it, well, I will put it in the lecture notes, but I would leave it to you to take this model and do the same calculation as in the fridge and see what should be the condition for it to act as an engine. And when I say act as an engine, I mean simply that you are biased more to go up than to go down. So this transition happens more often than the other one, and to see what that gives you. And you see that at that limit, you get the Carnot limit for an engine, which is the same as classical thermodynamics. Okay, and the last thing that I would say is, now that I finished the thermodynamics part, before I come back for the clocks part, I will update last year's lecture notes. For the lecture, for the parts that are not there, that even last year, so for instance, last year's lecture notes do not have stuff on entropy, not entropy, sorry, equilibration, for example. There will be new chapters, so I will point those ones out to you. But also in the existing chapters, I will also mark in a color and point out that I've updated some stuff, maybe with better explanations or more sort of background material or stuff like this. But I will update this before the clocks part, and then after the clocks part lecture, I will also do the same for the clocks one, which is already written from last year. All right, any more questions? None? All right then, thank you very much.